Hello everybody and welcome back. Root Beer here with question number 7 on the 2003 Euclid competition. So question 7, it's not the last I think of the two-parters, but it is the last of the two-parters that has, and it actually has the last of the light bulbs, but it's the last of the two-parters that has a light bulb and then written answer. We can see A has 2 written answers, 9 is just straight a written answer, and 10 is written answer, and it's got 3 parts. As you'll often find with 10s, I think 3 or 4 parts on a 10 is standard nowadays. Okay, but we're talking about question 7, that's all we're concerned with right now. So 7a, a regular hexagon is a 6-sided figure which has all of its angles equal and all of its side lengths equal. In the diagram, ABCDEF is a regular hexagon with an area of 36. The region common to the equilateral triangles ACE and BDF is also a hexagon. We can see it here. It's the shaded area. And we're asked, what is the area of the shaded hexagon? Okay. So, we're not given a whole lot. We're told that we've got a regular hexagon. Okay. And that it's got an area of 36. So, well, being that it's a regular hexagon, one of the first things that always comes to my mind is that the internal angles, the angles at A, B, C, D, E, and F in this case, are all 120 degrees. Okay, so I would probably start by taking this diagram and labeling a bunch of angles. And from angles, maybe we can work out some lengths, and from there, maybe we can work out the area of the shaded region. Now, I'm not entirely convinced of that. I don't know as we'll be able to compute the shaded region directly, because I don't off the top of my head know a formula for the area of a hexagon. If you do, that's great, and that's something that you might find useful in a question like this. But because I don't have a formula like that, I'm actually just realizing I probably can't work out what length AB is. I mean, yeah, great, we got an area of 36, but off the top of my head, I don't know how that relates to the side length of my hexagon. Oh well, so I'm just going to go with my first instinct, and that is to redraw the diagram and start messing around with angles. So just first off, because it's a regular hexagon, and I'll just make this note, if we have an n-sided regular figure, so a regular n-gon, it has internal angle of, and then there's a nice little formula, and now I'm trying to see if I can remember what is the formula. It's, so basically when we do the formula, I can't remember it off the top of my head, so I'm just going to rederive it. If we were to take a look at the interior angles, they're all going to be the same, and if we were to extend this line, we get a little extra bit, and we get a little extra bit, a little extra bit. And if we add up all these little extra bits, we've actually gone around in a full circle. All these little extra bits add up to a full circle. So each of these has got to be 360 degrees over how many of them? N. And the internal angle is 180 degrees. Subtract that. Okay? And we can double check this. If it were 3, we'd have 180 minus 360 over 3. That'd be 120. 180 minus 120 is 60. And the internal angle of a regular equilateral triangle is 60. We had 4 here. We'd have 360 over 4, that's 90. 180 minus 90, that'd be 90. So this does work. A regular hexagon, and this one pops up enough that you probably want to know this one just off the top of your head, not using the formula, has an internal angle of 120 degrees. 360 divided by 6 is 60. 180 minus 60 is 120. Pentagon is 108, if I recall correctly. And heptagon and higher doesn't really pop up. Maybe octagon, but nothing else really. And an octagon, I think, is 135. Anyways, enough about those sorts of angles. I also had a thought about the area. So if I have a regular hexagon, one of the things I can do is I can actually chop it up into 6 equilateral triangles. If this had area 36, each of these is a sixth, so these would be area 6. And I think from these triangles, having an area 6, we can work out the side length. And then we'd have the side of the hexagon. So that's just a correction to my earlier thought that I didn't think I'd be able to get lengths. Okay. But I originally said I'm going to take this diagram and I'm going to add angles. Oh dear. Oh, no, there we're good. I didn't go too far, did I? Nope, we're all set. Okay. So, we're going to redraw our picture here. And it's going to be, that's a terrible equilateral triangle. Or not equilateral triangle, regular hexagon. That's a little bit better. Okay. So every other point is connected up, and that got us these two triangles, and they overlap to create a hexagon. They didn't even specify in the question that it's a regular hexagon, so we might even need to show that. Okay, so I know that we've got a great big 120 degrees here, and that's true for every single angle here. We'll clean this one up a little bit. Okay, that's a little better. So we get 120s all over the place. That's fine. What can we do here? Well, I know that these side lengths are all the same as well. So it looks like these green triangles are all the same and they're all equilateral. Now what's the angle left over? We have 120 accounted for, so these two green angles must add up to 60. So they must each be 30. Okay. So we get an angle of 30 here, an angle of 30 here. And so that leaves us with an angle of 60 degrees in here for this triangle right here. Okay, so we also have, this is 30, and then this one is 30. So we've got another 120 here, and a 120 here, and a 120 here. We've got 120s all over the place. So that makes these 60s as well. And so we got 120s all the way around here. Okay. But notice, with this orange triangle here, we've now shown that it's equilateral. So that means, we'll use purple here, this length is the same as this length, is the same as this length. But this other triangle is isosceles, so that means this length, and this length, and all the purple lengths. So we can actually see that the shaded hexagon is also regular. Great. So if we had a formula for the regular hexagon in terms of its side length, I think we'd be all set. And we could do it that way. That would be a great way to do the question. Trying to see, is there a quicker way than working out a bunch of angles? Because I could probably get the red length, the red side length, the side length of the big hexagon. Sure. And then from there, we could probably use the sine law to get the purple length. Yeah. But, you know, trig isn't for everyone, so I was just trying to think if there's another way to do this. I think there is, and I'm going to let it mull in the back of my brain, and maybe I'll talk about it at the end. But I think we could probably do it with ratio between the side lengths or something like that. Okay. But let's concentrate on getting a formula for a regular hexagon in terms of its side length. So if we have a regular hexagon, we've got a side length A. And we connect up these sides. We're going to have 60 degrees everywhere. So we're going to have a bunch of equilateral triangles. In fact, we're going to have 6 equilateral triangles. So our hexagon area is 6 times our equilateral triangle with side length A. Okay, well now, how do we work out the area of an equilateral triangle with side length A? Well, I'm inclined to do a base times height sort of thing, so what's this height here? 60 degrees, 90 degrees, we're going to have 30 degrees. This is what we call a 30, 60, 90 triangle. They pop up a lot. And so opposite the 30 degrees, we got A by 2. And opposite the 60 degrees, we'll have root 3A divided by 2. Okay? 30, 60, 90 triangle, the side lengths have a ratio of 1 to root 3 to 2. This is something that pops up enough that you should just know. Okay? But if you needed to, of course, you could have just done something like sine law or other basic trigonometry. So its area is going to be base, which is A, times the height, which is going to be root 3 over 2A. And then we half it, 1/2 base times height. So we get root 3A squared over 4. So our hexagon has area of 6 root 3A squared over 4, or another way of saying that is 3 root 3A squared over 2. Okay, so now we can relate the area of our hexagon to its side length. We can figure out this red side. Then using the sine law, we can figure out the purple side, and then we can plug that into this formula here, and we'll be able to get the area of the shaded region. Okay, so let's connect that up, that, and the last one. There we go. Alright, so this red side length, what is it? We know that 36 is the area of the big hexagon, and so that's 3 root 3 all over 2 times this red length, which I guess I'll call R for red. So bring the 2 over, we'll get 72. Divide that by 3, we'll get 24. So 24 over root 3 is what R squared is. And we can simplify that to 8 root 3 is equal to R squared. And then I guess we just got to square root it. So R is going to be square root of 8 root 3. So there's a factor of 4 in there. We can bring that out as a 2. And then we've got square root of 2 and 4th root of 3. So that's not exactly a nice number. It's not exactly an ugly number. But I don't usually like seeing cube roots and 4th roots and 5th roots in any expression during a math contest. That usually sends up red flares that I've done something a little wrong. But we're going to keep it in there, and we're going to see what else we can do. Okay? So, now we want this purple length, because as we already demonstrated, we got an equilateral triangle here. Once we have this purple length, which I guess we'll call P, then we can just do 3 root 3 P squared over 2. And hopefully that'll get rid of this 4th power here. Okay? So our angles here are 120 degrees and 30 degrees. So 30 is opposite the purple one, 120 is opposite the red one. We can use the sine law. We can say R over sine 120 is the same as P over sine of 30. Okay. Well, we know what R is. That's 2 root 2 4th root of 3. Now how about sine of 120? Well, we do have a calculator on hand if we need it. but we could also just try and work out what sine of 120 is anyway. And it's going to be root 3 over 2. And p, we don't know what that is, but we do know what sine of 30 is, or at least hopefully you have that known. And if not, of course, you can grab your calculator. So we get 1/2 here. Okay. So, what can we do now? Well, we can cross multiply. We'll get 1/2 to root 2 4th root of 3 is equal to root 3 p over 2. Those guys will cancel. We can bring a 2 over, so we'll get 2 root 2 4th root of 3 is root 3 times p. And we can divide by root 3 on both sides. So the root 3, a 4th root of 3 is just the square root of 3. So we can get rid of that and put the 4th root of 3 there on the bottom. Okay, so now we know what p is, that purple length. We can plug that into our area of a hexagon formula. So it's 3 root 3 p squared all over 2, if I'm remembering correctly. So let's just double check. Yep, everything looks good. And now p, we can plug that in, and that's 2 root 2 over the 4th root of 3, square that, all over 2, we get 3, a root 3, and we'll get 4 times 2, we'll get a root 3 on the bottom, and that'll all be over 2, so 2 of the 2's will cancel out, the root 3's will cancel out, and we're left with 3 times 4 is equal to 12. Okay. Now, I said I thought I saw another way of doing it, so let me just briefly see if it's going to work out. But I think I'm validated by the fact that eventually we're able to show that, basically we've got, over here we were almost able to show that r is just root 3 times p. Okay? We did have that at one point, and I think that is sort of key. We don't actually need to work out r and p. So if we just stop for a moment and were to take a look at our red length and that purple length, okay. If I can find a ratio, let's call this, side length r again. If I were able to find that this length, the purple length, is something like q times r, knowing that the shaded region is a hexagon, a regular hexagon, these two figures are similar. So 36 is to the area of the shaded region, as r squared is to qr squared. So the ratio between the side lengths gets squared because area requires sort of two side lengths, 2 dimensions to work out. So we square these things. So we were able to show that this should be root 3r, or sorry, 1 over root 3r. And you could probably work that out by other means than just doing sine rule. So really, the area between the big hexagon and the shaded hexagon should be 1 to 1 over 3. So the area of the shaded region should be 1/3 of 36. So area of the shaded region is again 12. Okay? And there's probably a bunch of different ways to show the ratio between the big length and the small length. Okay? I'm not going to get into them. Obviously one of them is to use the sine law. There's probably, I think I spotted, this guy right here is a right angle triangle. And, oh yeah, this is a right angle triangle. This is 60 and this is 30. So r to QR is also up here, 30, 60, 90 triangle, this has got to be 1 root 3 of r. So there's another way to do it. But we got a B part, so let's not dwell. Let's take a look at our B part here. Okay. At the big top circus, Herc, the human cannonball, is fired out of the cannon at ground level. For the safety of the spectators, the cannon is partially buried in the sand floor. Okay. Herc's trajectory is a parabola until he catches the vertical safety net on his way down at point B. Okay. Point B is 64 meters directly above point C on the floor of the tent. If Herc reaches a maximum height of 100 meters, which they kindly have labeled for us here, directly above a point 30 meters from the cannon, determine the horizontal distance from the cannon to the net. So we want cannon to this point C. Okay. So the nice thing here in this question is we have a parabola. That's Herc's path. And we can almost sort of see that the ground level might stand in for an x-axis. And I think we could probably get the equation of a parabola from here. I'm just trying to think of the best way to set it up coordinate-wise. Should the cannon be 0, 0? Should the point directly below the apex be 0, 0? I think I'm going to go with the point directly below the apex. So the cannon will be at minus 30, 0. Okay. It's a written question, so let's just talk about this. So we can introduce coordinates so that the ground below the apex of Herc's trajectory is 0, 0. And the cannon lies at negative 30, 0. So our x-axis is exactly the line they gave us in the middle. The apex here is 0, 100. The cannon fires here at negative 30, 0. And we have ourselves a parabola until we hit a safety net. And that will be at some point, some distance here, x. That'll be at x64, where x is positive. So we want the distance between the cannon and the net. That's a distance of 30. We want 30 plus x. That's ultimately what we want. And we'll label here our net. Okay, we might want to explain what x is. Where x is the distance from the apex to the net along the ground. Not, say, measuring the curve from the top to the net. Okay. So we've introduced our coordinates using these coordinates. we can see the apex, or the vertex, of our parabola is at 0, 100. So if we use vertex form of a parabola, the trajectory has equation, well, vertex form looks like a x minus h squared plus k, where hk is the x and then y coordinates of the vertex, and a is an appropriate scaling factor. We don't know what a is yet, but x minus 0 squared plus 100. And so we can simplify that to just ax squared plus 100. Maybe I shouldn't have used x here, just because I've got x's in my equation, so I'm going to say d. And I'll go back and change that as well. D for distance. Okay. So we need to finish this equation. We need to figure out what a is. Now, fortunately, we have another point, negative 30, 0. And that will help us scale this appropriately. We'll plug in negative 30, and we should get 0 out. And then once we have that equation, we want 64 as our y-coordinate, so we set that up and solve for d, and d will be the positive value because we've crossed past the apex. There is another point that has a y-coordinate 64, but that would have the net placed before he reaches the top of his trajectory. Okay, and that would be at negative d. So we specifically want the positive d value. So we know that negative 30, 0 is on our parabola. So 0 is equal to a negative 30 squared plus 100. Negative 30 squared, why that's 900, so we have 900a plus 100. And we can bring the 100 over to the other side. 900a. Divide those two, and we can see pretty quickly we're going to get a is negative 1/9. Okay. So our equation is y equals negative 1/9 x squared plus 100. To find d, we take the positive solution to y equals negative, or not y, 64. Equals 1/9 x squared plus 100. So let's rearrange that. The 100 will come over to the other side. We'll get negative 36 is negative 1/9 x squared. We can get rid of the minus signs, and we can multiply by 9 on both sides. So getting rid of the minus signs and multiplying by the 9. 9 is 3 squared. 36 is 6 squared. So combined, they should be 3 times 6 all squared. So that's 18 squared. So that should be 324 is equal to x squared. So x is plus or minus 18. So our distance here, d, is 18 meters. So again, we want the positive value. And let's just double check. We did want the distance, horizontal distance from the cannon to the net. So the distance from the cannon to the net is 30 meters plus 18 meters, and that's 48 meters. And we're all done. Okay. So that was question number 7, and I look forward to question number 8, where both parts are written, and hopefully you do as well. And I'll see you guys for that video next time.